Hello everyone, this is Lecture 9 of ComSci 123, Priority Queues and Heaps. In today's video, we will look at another ADT called the Priority Queue and look at how to implement them using the sorted and unsorted DLL. We will also look at heaps, which are data structures that are used to implement priority queues. Okay, so let's start. So we are already on our 10th ADT for ComSci 123, which is the priority queues. Now, we've already seen queues before, right? And we said that queues are linear ADTs which follow the first in, first out principle. So whichever item is added first to the queue will also be the first item that would be taken out. Okay, so some of the methods for the queue were size is empty, and then in queue item to add items to the queue, the queue to remove the front item, and front to just look at the front item without removing it. Okay, so we're already familiar with the queue. However, in some cases, the first in first out principle is not enough. So let's say, for example, in these scenarios, first in first out might not work. Okay, so for example, in the air traffic control center, wherein they are directing airplanes, okay, in the airport. So usually you make the planes land depending on their arrival, right? So whoever arrived first would also be accommodated first. However, there are some other factors that need to be considered. Like for example, what if the terminal that they are, or the gate that the plane is supposed to go to is not yet ready, right? So they will have to be postponed or delayed a little bit. Or when a plane already is calling for a stress signal, like it's already low on fuel, or something else is happening, so that plane might be given higher priority in landing, right? Another example is the lines or the queues in amusement parks. So usually when you line up to go on a ride, it's first come first served. However, there are VIP lines also, or like priority lines, wherein you can skip the long line if you paid for a VIP ticket, right? So you can skip the long line and go straight to the front. Okay, so that's also possible. And then lastly, for to-do lists, usually when you create a to-do list, so you write them one by one, right? But then you try to prioritize the tasks that are more important. So for example, when the deadline for this task is already coming up soon, then you have to prioritize that even though you added it later, right? So even if it's like number 10 on the list, but if it has higher priority, then you have to focus on it, right? So in some cases, first in first out makes sense, while in some cases you need to consider the priority of certain things. So that is the idea behind priority queues. Okay, so a priority queue is just a dictionary that follows the smallest key first out principle. Okay, so a priority queue is just a dictionary, right? So when you have a dictionary, then you have entries with a key value pairs, right? So, and because it's a dictionary, you are allowed to have multiple entries with the same key. Okay, now what is this smallest key first out principle? So in priority queues, our keys refer to the priority level of this entry or that item, okay, and the value is the item itself. Okay, so it tells you whether that item is of high priority or of low priority. Okay, so the key will tell you that. And usually the smallest key will be given the highest priority. So the lower the key is, the higher the priority. Okay, so that is what we mean by smallest key first out principle. So the highest priority is the one with the smallest key. Okay, so a priority queue will look something like this. So a normal queue will have a front and a back, right? So maybe this entry here 10A was added first, and then next was C2D 0D, and then 1B, right? However, we will not remove it according to the first in first out principle. So even if 10A was added first, it has a low priority because of the high key number, which is 10. So the lowest key here is 0, associated with the entry 0D. So this entry here will be removed first, because even if it is somewhere at the back, okay, so it was added a little bit later, but it has the highest priority because it has the lowest key. So when we remove the item from the priority queue, we will be removing the one with the lowest key, or the highest priority. Okay, so that is the difference. So it's not whatever is in front will be removed. It would be whatever has the highest priority will be removed. Okay, so that's priority queues. So we notice here that keys are actually kind of versatile, right? So the in entries you have key value pairs. So keys are not only used to identify the entry value, but they are also used to rank entry values. So in the normal maps and dictionaries, we used keys to identify the value, right? So to pair them with the value. But for priority queues, the keys are used to rank the values, okay? So to give priority to them. So keys are usually assigned to the item by either the user or by the application. So it could be system generated, or it could be given by the user itself. Okay, but the keys are not necessarily related to the item's content, okay, or the value itself. So let's see some examples of keys. So let's say, for example, phone book. In the phone book, your key would be the name, and then the value would be the phone number, right? So in this case, the name is given by, well, the person itself, the user of the phone book. Okay, so you have a meaningful key because that is used to identify the phone number, which is just a bunch of random numbers, right? So for you to not memorize the phone number, you can look it up through their names. Okay, so that is a meaningful key. Next, we have student records. So for example, student records, you have the student number as the key, and then you have your student records as the value. So in this case, the student number, which is just a bunch of random numbers generated by your school, does not really relate to the student record. So if you have a student record of 0001, that doesn't mean that you are like, you have good grades, right? So it doesn't really mean anything, right? It's just a number that was assigned to you when you enrolled at the school, right? So it's not related to the value. And then finally, you have callers queue, for example, in call centers or hotlines. So some callers might be prioritized better because they are VIPs or whatever. So the priority level could be the key, and then this is an example of when we use keys to rank items. Okay, so keys are not only used to identify your values, but they can also be used to rank your values, especially here in our priority queues. Okay, so those are keys. So going back to our priority queues, so we said that we follow the smallest key first out principle. But what if there are ties? Okay, so for example, there are multiple entries that have the same key, that is the smallest key, right? So what should you do? So you can do one of two things. You can either just remove any entry with the smallest key. So for example, there's an entry with key 0A, and then there's 0C, and then 0 is the smallest key. So you can just remove any of them, or you can also remove the smallest key entry that was added first. So you could use the first in first out as the tiebreaker if you want to. But either way, it doesn't really matter, because if they have the same priority level, then it shouldn't matter whether you give entry A or entry B, right? Because they have the same priority level anyway. Okay, so that is for the tiebreakers. So now let's look at the methods or the interface of the priority queue ADT. So as usual, you have the size and is empty. So size will return the number of entries in the priority queue, whereas is empty will return true if there are no entries in the priority queue. Okay, so this is pretty straightforward. Okay, so the more important methods are the following. So first, you have insert kv. So you have insert with you pass in two parameters, the key and the value. So the key is what gives you the priority level, and then the value, of course, is the item itself. So insert will just add a new entry with the key k and the value v to the priority queue. So the simple insert. The next is min, the min method. So it will return the entry in the priority queue with the smallest key. Okay, so basically this is um, the equivalent of front. Okay, but instead of front, give me the minimum. Okay, the minimum entry, or so the entry with the smallest key. Okay, so you'll just return it without removing. But if you have remove min, then you remove and return that entry with the smallest key. Okay, so min and remove min are similar, but the difference is that remove min, of course, removes that entry from the priority queue. Okay, for both of them, min and remove min, it will yield an error if the priority queue is empty, because of course there is nothing to return, right? There's nothing to remove, or there's nothing to return when there is no entries in the priority queue. Okay, so those are the 5 methods. So the important ones are insert, min, and remove min. Okay, so those are the methods for the priority queue. Okay, next let's look at how to implement the priority queue. So we'll look at two main implementations, and that would be the unsorted DLL and the sorted DLL. So this is not about array versus DLL anymore. So we'll stick with DLLs for our implementation, and what we will compare would be the unsorted version and the sorted version. Okay, so let's start with unsorted DLL. So for the unsorted DLL, it's pretty straightforward. It's pretty simple. You use an unsorted DLL to implement the priority queue. So the DLL nodes will contain the entries of your priority queue. For unsorted DLLs, the behavior of this implementation would be your insertions would be fast, but your calls to minimum and remove min would be kind of slow. And I'll tell you why in the next slide. Okay, but that is the strength of unsorted DLL. It has fast insert, but the downside is it has slow min and remove min. Okay, so how do we do it? So for unsorted DLL, so since it's unsorted, we don't need to sort the entries in any manner, right? So we'll just arrange them like a first in first out manner. Okay, so we'll just arrange them in the order that they were inserted. So we will insert, we'll add the new DLL node with the entry at the back. Okay, so before the tail guard. Since this is a DLL, there are sentinel nodes, right? The head guard and the tail guard. So if you insert at the back, this will be inserted before the tail guard. And inserting at the tail guard is pretty straightforward. You'll just need to link up 4 things, right? So that would be constant time, O of 1. Okay, so that's why the insert is fast, because you can just insert it at the back, which doesn't take any time. Yeah, so the other 2 methods are min and remove min. This 2 actually requires linear search. Why is that? Because since your DLL is unsorted, so you need to know where the minimum entry is, right? So the entry with the smallest key. But since it's unsorted, you have to actually find it throughout the DLL, right? So you need to traverse starting from the head guard all the way to the tail guard to find the entry with the minimum key. So you need to inspect each entry. So is this the minimum? And then you keep track of the current minimum, and then until you reach the end of the DLL, and then whatever current minimum you have by then that would be the actual minimum key. Okay, so since it requires traversal from head to tail, that is linear search, then it will take you O of n time. Okay, so that is the downside. Since you did not sort it, then you will have to look for the actual min key, right? So that's why it takes O of n. Okay, so that is unsorted DLL. So it looks something like this. Okay, so insert can be easily done at the back. Okay, you'll just add more items here at the back, but when you remove the min, or when you find the min, you actually have to go through each node here to make sure. So you start at the front is for the min, so currently it is, and then next is 2, so you update the current min as 2, and then you go to 0, current min is 0, and then at 1 it's still 0, and then you reach the tail guard. So the min entry is the one here with key 0. Okay, so it entails a linear search from the head guard all the way to the tail guard. Okay, so that is unsorted DLL. Now let's look at the other implementation, which is sorted DLL. So for this one, we will implement the priority queue still using a DLL, okay, a doubly linked list. However, this time the entries will be sorted according to their keys. So at all times, we will keep the DLL sorted. Okay, so whenever we insert, we have to keep the sortedness of the DLL. Okay, so because the DLL will be sorted, the entry with the smallest key, or the min key, will always be at the front. Okay, so it's always after the head guard. Okay, so that is the advantage of your sorted DLL. So the strength of sorted DLL is that your min and remove min will be fast, because you can always just look at the front node, okay, the one after head guard, and then you can either return that if it's min, or remove that if it's remove min, right? However, the downside is that it will have a slow insert operation, because you have to keep the DLL sorted. Okay, so I'll show you why. So for insert, you need to find the appropriate location to keep the DLL sorted, right? So if it's a new entry, you have to actually look for the correct location, or where should you insert it, so that the DLL is still sorted. So you can't just insert it at the back, right? So to keep the DLL sorted, you have to look and probe each node. So can I insert it here? Can I insert it here? The next one, and then when you find it, that's when you insert it at that position, right? And then inserting at the middle is pretty straightforward for DLLs, because you'll just have to relink the nodes, right? So the inserting is not the problem, it's the looking for the correct position to insert it into. Okay, so we have to do linear search, because at the worst case, we traverse from the head guard all the way to the tail guard, and then find that we have to insert it at the tail guard. And that happens if you insert the new max key, for example. So let's say you have 0, 1, 2, 3 only, and then you insert 5, so that would be added at all the way up to the end, but you don't know that at the start. So you have to probe, can I insert it after 0, after 1, after 2, after 3, after 4, and then you find out that you actually need to insert it all the way to the end. So that's why it takes O of n, because you need to do linear search to find the appropriate location to keep the DLL sorted. Okay, so that's the hard part for sorted DLL. The easy part is min and remove min, because you just have to look at the DLL node at the front, which is after the head guard. So that just takes O of 1, or constant time. Okay, because it's always at the front, because you keep it sorted. Okay, so yeah, that's sorted DLL. So it looks like this. Okay, so let's say that A was added first, so K4, and then B was added next. So since it has a higher priority, it's added before 4A, and then next, let's say, is C. So K0, it's added all the way at the front because it has the highest priority, and then D with priority 1 is added after it because it has a lower priority than K0, right? So if you want to remove min, then it's always at the front. But if you want to insert, then you'll have to insert somewhere in the middle or wherever the appropriate position is to keep the priority sorted. So you have 0, 1, 2, 4 in sorted order of priority keys. Okay, so that is sorted DLL. So between the two, which implementation should you use? Well, it actually depends on the situation. So for unsorted DLL, this is appropriate when you need a lot of inserts, because the strength of unsorted DLL is that the insert operation is efficient and fast, right? So you use this when your priority queue is dynamic, in the sense that it's always adding entries. So when it's always adding new entries from time to time, so you go with the implementation wherein the insert is efficient. So since you're always just adding at the back, then this one is good to use. And you also use this when you expect that you will only use a few min and remove min operations, okay, since they are the ones that are kind of slow to run, okay. So if you're expecting only few min or remove min operations, then unsorted DLL is appropriate. On the other hand, for sorted DLL, the strength is in the min and remove min, right? So they're efficient. So you use this when the priority queue is loaded once. So you already have all of the entries at the start, and so you insert them all at once, okay, and then there's not much insert after, and then you're expecting a lot of min and remove min operations. So that is when sorted DLL will shine, because min and remove min is its strength and not the insertions. So if you have a pretty static priority queue wherein you only load all of the entries at the start and then you don't really add more entries later, so sorted DLL is much better. Okay, so those are the two priority queue implementations: unsorted and unsorted and sorted DLL. Okay, now why did we not use arrays? Okay, so for arrays, the problem is when you insert or remove at the middle. So you've already encountered this a lot of times, right? So when you insert or remove at the middle of an array, the problem is you have to shift entries forward and backward, right? So to make room for the newly insert or the entry that you need to insert, you need to move entries forward, right? Or you need to move entries backward when you need to fill the hole that was left by the remove operation. So that is the disadvantage when you use arrays. Whereas if you use DLL, linking of the nodes is pretty straightforward, even if you insert or remove at the middle. So that is why we focused on DLLs instead of arrays for this implementation. So anyway, the focus of this is not whether it's a DLL or the array. The focus of the implementation comparison was whether sorted or unsorted was good for which scenario. Okay, so that is the first two implementations of priority queues, unsorted DLL and sorted DLL. So let's now go to the next one, which is heaps. And heaps will also be used to implement priority queues later on. So what are heaps? Okay, so these are not the heaps that we are talking about. So it's not the heap like a pile of stuff, or the heap like the body part, or hip like hipsters, or heap like hip hip hooray. So it's not this heaps. So what are heaps? So a heap is basically just a binary tree. Okay, so we've discussed binary trees in the previous video. So it's a tree with at most, wherein each node has at most two children, right? And we call it the left child and the right child. Okay, so a heap is a binary tree that is used to implement priority queues, and it's also used in heap sort. So if you're familiar with sorting algorithms, there is a sorting algorithm called heap sort that uses the heap data structure. Okay, so in heaps, the nodes in this tree, or the heap itself, will store the keys of the entry. Okay, so since we'll be doing some comparisons, it should be numeric, right? Or even if it's a string, there should be a way for you to compare the keys so that you can sort them. Okay. There are two main types of heaps. You have the min heap and the max heap. But for this discussion, we'll focus on the min heap. Okay. The max heap is basically just the opposite of the min heap. Okay. And for the heap, the min heap that we'll be using to implement priority queues, it follows two properties, or it maintains two properties. You have the min heap order and the complete binary tree property. Okay, so let's take a look at these two properties. So the first one is the complete binary tree property. So a heap must always be a complete binary tree. Okay, so this is a structural property. It talks about the structure of your heap, or the binary tree itself. So we've already mentioned complete binary trees in the previous video, and to recall, this is when the binary tree is completely filled, okay, at each level, except maybe for the last level. Okay, so the last level is the exception, and when the last level is not completely filled, it must be filled from left to right. Okay, so there must be no holes in between. It should be filled from left to right. Okay, automatically all complete binary trees are also balanced, or the leaves should be at depth h, the last level, or h minus 1, which is the second to the last level. Okay, so a complete binary tree looks like this. So you'll notice that at level 0, so you have the root. At level 1, so all two nodes are present. At level 2, all four nodes are present. And then at the last level, it's not completely filled, right? But you fill it from left to right. Okay, so if you were to add a new node here, it would be added here next, and then after that it would be added here. You cannot add here because you need to do it from left to right without any skips. So adding here would be a violation of the complete binary tree property. Okay, and as long as you haven't filled this previous level yet here, you also cannot add at the next level. Okay, so you can't add nodes here if the previous level haven't been completely filled up yet. Okay, so you have to completely fill out the previous level before going to the next level. Okay, and then the last level is the exception, wherein it could have some nodes and then it's not completely filled up. But when there are nodes in the last level, it should be filled from left to right. So there should be no like nodes here where when there are spaces here that haven't been filled up yet. Okay, so that is a complete binary tree. Okay, so it talks about the structure of the heap. Now the second property that the heap needs to maintain is called the min heap order. Okay, so this is a relational property, and this refers to the arrangement of the keys inside the heap. Okay, so since we know that the nodes store keys, right, so we'll have to set a rule about how to place the keys in relation to their parents or their children. Okay, so it's a relational property. So for the min heap order, it states the following. So the node's key should be greater than or equal to the node's parent's key. Okay? So if you're a child, your key must be greater than your parent. Okay, greater than or equal. Okay? So, in other words, the children's keys must be greater than or equal to the parent's key. Okay? So, how does that look like? So, for example, here, um, so, for example, here, 5, or maybe let's start here. 16 and 25 are both greater than the parent, which is 15. Right? So, you have key of children must be greater than or equal to the key of the parent. Okay? And then here, 14 and 12 are both greater than 9. Okay? And then 11 and 13 are both greater than 7. And then in the next level, you have 15 and 9 are both greater than 5. Okay? 7 and 20 are both greater than 6. Okay? And then finally, 5 and 6 are both greater than 4. Okay? So you'll notice that the smallest key should be at the root. Okay? So you have 4, 5, 6. All of the other keys here are greater than the one at the root, which is 4. Okay? So that is min heap order. Okay. So it also has the following property. So any path from the root going to any leaf node, you will encounter keys in non-decreasing order. So you can think of it as increasing or equal. Okay, so it must be non-decreasing. So it could be increasing or equal. Okay, and as I mentioned, the minimum key will always be at the root of the heap. Okay, because the parent must be less than or equal to the key of the children, right? So the smallest one should be the grand or the greatest ancestor of them all, which is at the root. Okay, so going back here, so any path from root to leaf would be non-decreasing or increasing. So let's check that. So from 4 to 16, so this is these are the leaf nodes, right? 16, 25, 14, 12, 11, 13, and 20. So those are the leaf nodes. So let's check the paths if they are indeed non-decreasing or increasing. So 4, 5, 15, 16, so that is non-decreasing. Then you have 4, 5, 15, 25, that's also non-decreasing. And then 4, 5, 9, 14, also non-decreasing. And then you have 4, 5, 9, 12, that's also non-decreasing. 4, 6, 7, 11 is non-decreasing. 4, 6, 7, 13 is also non-decreasing. And finally, 4, 6, 20 is also non-decreasing. Okay? So that is following the min heap order. So again, the smallest key is at the root. Okay? So those are the two properties that the heap needs to maintain at all times. Now, about the height of the heap. If the heap has n keys, then the height of the heap would be the floor of log of n base 2. Okay, so let me show you examples of that. So, for example, if you have 0 nodes, then the height would be obviously 0 because there's nothing. But if the height or if the number of nodes is 1, so let's say just the root, okay, so the height of this is 0. So even if you have one node, the height is 0 because there are no children. Okay, so you measure height by the number of like this one, the edges. Okay, so this one is height 1, this one is height 2 because you have two levels. So from here to here and from here to here. So that's two levels. So that's height 2. But if it's only the root, then that's height 0 because there are no children. Okay? So this is height 0. Now if you have two nodes, it would look like this, right? And then if you have three nodes, it would look like this. So that is height of 1. So from 2 to 3, height of 1. And then you have 4 to 7. So that's, you already have three nodes, right? So that you have 4, 5, 6, and then 7. So all of that will have height of 2. Okay? So even if it's a completely filled or not completely filled, the height will still be 2. Right? And then after 7, you have 8 to 15. So you have 8. That's still height 3 already. Right? Because that would be that's the max depth of the tree. 9, 10, 11, 12, 13, 14, and then 15. So that's still height of 3. And then for 16 to 31, that would be height of 4. So that would be 16, 17, and so on. Okay, I will not continue that anymore until 31 nodes. It would be height of okay. So you have here the limits are 1, 2, 4, 8, and 16, and you'll notice that is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. So that's why if you have log of n base 2, that would be the height. Okay, so you have the 0 here, the 1, 2, 3, and the 4. And then those that are not exactly powers of 2, you just take the floor, right? So that's why from 4 to 7, it's still log of 7 base 2 is like 2 point something, right? So if you take the floor of that, it's still 2. So as long as it doesn't reach the next level yet, like the 3, then we'll take the floor and it will still be height of 2. Okay? So that is so it's important to remember this, that the height of the heap is log of n base 2. Okay? So that is the height of the heap. And then next, so let's take a look at how to insert new keys to the heap. Okay, so let's say that this is our current heap. So this is our last node. Okay, 29. So we'll call that last node W. And then where will we insert our new key, for example? So if our new key is K, for example, where will we insert it? So we'll insert it to the next available leaf position. So since we're supposed to fill this from left to right, okay, so we're from here to here. So the next available position is this one, right? So we'll call that Z. So W is the last node. Z is where we will insert. Okay, so that would be our names for those two positions. So so this is where we'll insert, right? Z. So we'll insert K there. But then for whatever value of K, this might violate the min heap property. So we'll actually do something called the up heap algorithm, which I'll show you later, to make sure that the min heap property is still being imposed. Okay, but I'll show you that in a later slide. But just know that we'll have to find the correct position to insert it into, which is basically following the complete binary tree property. So fill this from left to right, and then after that we also need to make sure that the min heap property is being followed still. So we'll do the up heap. Okay, so this arrow up here. So I'll show you the details of how to do that in a while. So how will you do insertion? So we need to preserve the complete binary tree property. So to do that, so we mentioned that W would be what we call the last node, okay, and Z is where we'll insert the node. So if W, or the last node, is already the rightmost node on its level, then you cannot add any more to the right because it's already the rightmost. So what we'll do is we will have to insert on the next level below, and we'll add that at the leftmost part of the next level. Okay, So Z is the leftmost node on the level below. Otherwise, if it's not, if the last node is not yet the left, if the last node is not yet the rightmost node at that level, then Z, or where we will insert, would be the immediate right position of the last node. Okay, so if that seems like a mouthful, I'll show you an example. So here in the first one, the last node is 10, right? Since you only have 3 nodes. So 10 is already the leftmost node here at this level. So we can't add any more nodes at this level. So if we want to add a new key, then we'll have to add it at the next level, at the level below. So we'll have to add it at this level here, and we'll have to add it at the leftmost level. So it would be the left child of 14 right here. Okay, and then as I mentioned, we'll be doing up heap, but for now we will shelf that operation. So on the other hand, if for example we've already added something like 29 here, this is not the rightmost node, so there's still some positions that are available in this level. So immediate right of 29 would be this position here, and then if this one is filled already, the immediate right is this position here, and then after that would be this position here. Okay, and then after this is filled in, so this level is already full, then we'll have to add on the next level again. Okay, so basically what this tells you is that just follow the correct order. So this would be like this, and then next level like that, and then here starting from left to right again. So like that. Okay, so that is how we insert. But again, where we insert the key might not be the correct position for this key, because like for example, what if this is key 5, right? So 5 is a child of 14, so this violates the min heap property, because the parent should be less than or equal to the child's key, right? So that's why we it's necessary to do this up heap algorithm. So we have to do that because we need to preserve the min heap order property. Okay, so after storing the key, the new key k in that position that we found, we have to do the up heap algorithm. So what is the up heap algorithm? So it works like this. So let's say that 5 is where you inserted it into. You have to compare 5 with its parent. Okay, so 5 versus 14. So supposedly the parent should have the smaller key, right? So if that violates the min heap property, then you have to swap them. Okay, so 5 is smaller than 14, so we'd have to swap them. So here 5 is already at the top, and then 14 is at the child. But then we have to continue doing that, because what if this one is even smaller than its parent? So next we'll compare this 5 with its parent, which is 7, and it turns out 5 is smaller than 7, so we also need to swap it. So 5 eventually ended up at the root. Okay, so from here where we inserted it, it ended up at the root after doing the up heap. Okay, but if it doesn't violate the min heap property, then there's no need to swap also. Okay, so we can stop early. If for example, what if this was 3, like what if this was a 3 here? So if we compare 3 and 5, this is already the correct position, so there's no need to swap anymore. Okay, so yeah, so we only swap if it violates the min heap order. Okay, so these are the steps. So you compare the key of the node Z and the key of the parent of Z. If the key of the node is less than the key of the parent, then we have to swap them, because supposedly the parent needs to have the smaller key, right? So swap the node Z and its parent, and repeat this until there are no more min heap violations, or when you reach the root, because then the root has no parent, so you have to stop there. Okay, so that is the upheap bubbling algorithm, which preserves the min heap property. Okay, so that is for insertion. Now, the upheap procedure restores the heap order property along the branch that we are looking at. But how about the other branches? Okay, how about the sibling? Will it still be okay? Okay, so it turns out that we don't need to worry about the sibling branches. Okay, because here, um, for example, 5 and then 14, so this two will be swapped, so this will be 5 and then this will be 14, right? And then before we added this, so before we added 5, so when this was not yet existent, the whole tree was already a min heap, right? So 7, 14, 10, and then 29. So we know that this one and this one are already following min heap, right? So 29 is greater than 14. Okay, now with the addition of 5, and then we swap it with 14 here, so this becomes 5 here and 14. Now the fact that we swap them means that the newly added key was actually lesser than 14, right? So it's still safe because 5 is still less than 29 and 14, which are its new children, right? So if you have 14 here and then 5 here, 5 is still safe here because 29 will still be greater than the parent, which is 5. And then once we swap this 2 here as well, so when we have 7 here and then 5 here, so 7 and 10 are still both, so when we have 7 here and then 5 here, so 7 and 10 are both greater than 5 still. So the other branches can just sit still and do nothing because they will not violate the min heap property. Okay, so yeah, so that is insertion. Okay, let's see one more example of upheap. So from start to finish. So let's say that this is our current heap here at panel A. So we'll have to insert the new key, which is the new entry is 2t, so the key is 2. So we'll have to insert it here, right? So that's why it's added here. And for the upheap, we'll have to compare this 2. Is 2 less than 20 its parent? Well, yes. So that's why we have to swap them. Okay, so we swap them here at panel C, and then now 2 is here and 20 is here. Okay, now we'll continue. We have to compare. Should we swap 2 and 6? Well, yes, because 2 is less than 6, so it should be at the parent. Okay, so we'll swap 2 and 6, and right here, so 2 and 6 are swapped. So 2 is now at this node right here. So 2 is at this node and 6 is at this node. And then while we're here, we also have to check, should we swap 2 and 4? Well, yes, because 2 is still less than 4, and 2 should be the parent node. So we'll also swap it here, and we have 2 at the root and then 4. And then if you'll notice, everything still follows the min heap property, right? Now if we add another entry here, like let's say 8, or maybe not 8, maybe 5. If we add 5 C as the new entry, if we add 5C as the new entry, then we'll have to add it here, right? Because that is the next available position. So 5C, 5 will be swapped with 6, so 6 would be here, 6Z, And then 5, should we swap it with 4? Well, no, not really, because 4 is already less than 5. So this is now our new entry after adding 5c. And you'll notice, even if 5a and 5c have the same what do you call this, the same priority level, which is 5, they are at opposite ends. Like this one is at the left half, this one is at the right half. And that's fine, because as long as everything still follows the min heap property, then there should be no problem there. Okay, so yeah, so that is the example for up heap. So now let's talk about the performance of insertion. So at the worst case, you will do the bubble up from the last level all the way up to the root, which is what we did at this example, because we started here and then we ended up all the way to the root, right? So if we do swapping from the last level all the way to the root, that would be equal to the height of the heap, right? So since you're doing one swap at each level, that would be O of h, or the height of the heap. But since we established earlier that the height of the heap is log of n base 2, so if the running time is O of h, because we're traversing from the root to the leaf, or from the leaf to the root in up heap, and it's taking the whole height, and if height is log of n base 2, then the running time of insert is O of log of n base 2. O of log n, basically. Okay, so it's faster than the sorted DLL's insertion, because sorted DLL insertion was O of n, right? Because we had to traverse the whole DLL to find the correct position to insert into. So at least the insertion here is faster because it's log of n base 2. Okay, so that is insertion in heaps. Now, how about removal in heaps? How about if you want to remove the minimum key? Okay, so you need the entry with the smallest key, and it's easy to find the entry with the smallest key because you can just find it at the root. Okay, so since we arranged it in a heap, in a min heap to be exact, then you can always find the smallest key at the root. So you can just access the heap's root and retrieve its entry if you want to remove it. However, we cannot just remove the root node itself, right? Because then it would break the whole tree. There will be no parent for the two root children. So instead of deleting the root entirely, what we will do is we will replace it with the last node's entry. Okay, so this is a quick example of heap removal. So let's say that 5 here is our root node. So this is the min key. So this is what will return, right? 5. So after removing that, we cannot just leave the root node empty because, well, that won't be a heap anymore. So what we'll do instead is find the last node. So since we have so the last node here is 14, right? And then we will copy whatever is the value of the last node to the root node. Okay? And then since this node here previously has been copied already to the root, then we will just remove this node here. So it becomes a blank. Okay? So we'll remove this node here after copying its content all the way to the root. But now the key that we copied to the root might not be in its correct position, so we'll also do something called a down heap algorithm. Okay, so the opposite of up heap. Okay, to fix the position or the to make sure that the min heap property is being enforced. Okay, but that's the basic idea. After removing the root entry, replace it with whatever is at the last node, and then do the down heap thing. Okay, So store the root entry to a variable because you need to return that later. Okay, and then let W be the last node of the heap. So since we're always keeping track of the last node, so it's easy to do this. And then we'll copy whatever is the entry of the last node to the root. Okay, so we'll overwrite the root node so it's already removed. Okay, and then we'll do the down heap algorithm to make sure that the min heap order is being enforced. So what is the down heap algorithm? So the down heap bubbling algorithm will start from the root because this is where we added the last node's entry, right? And then from the root, we'll compare it with one of its children, the child with the smallest key or the smaller key. So between the two, 7 and 10, which has the higher chance of being the new root. So it has to be 7 because it's smaller than 10, right? So compare 14 and 7. Should we swap it? Well, 7 is smaller, so yes, we need to swap it. So 7 becomes the root and then 14 becomes the child. And then we'll continue going down because 14, this might still be the correct position for 14. And then we'll consult it. 14, it only has one child now, which is 29, so we'll compare it directly with 29. 14 and 29, should we swap them? Well, not anymore because 14 is actually less than 29. So we won't swap here, and then that is already the correct min heap order, right? So 7 is less than 14 and 10, and then 14 is less than 29. Okay, so that is the idea for the down heap bubbling algorithm. So for the details, let P be the parent or the current node. So that is the node that we're looking at. At the start, this will be the root node because that is where we start our down heap. And then let C be the child of the node P with the smaller key. So between the two siblings. So for example, if this is your node P and it has two children, like let's say 3 and 2, so which between the two children should be child C? It would be 2, so this would be C. Okay, because it has the higher chance of replacing the parent node because it has the smaller key. Now if it has only one child, like say 4, then automatically you have to compare it with this child because there is no other one, right? So C is the child of the node P with the smaller key, and then you'll compare P and C, okay, to check if you need to swap or not. So if the key of the parent is greater than the key of the child, then we need to swap the two because the key of the parent must be less than or equal, right? And then we'll also repeat this going down until there are no more min heap violations, or if we reach a leaf node. So if we reach a leaf node, there are no children anymore, so we can't compare. Okay, so we'll stop there. Okay, so we'll go down, repeating this procedure until there are no more violations so that we can preserve the min heap order property. Okay, so that is down heap bubbling algorithm. So let's see one more example. So in here, 4C is the current root node, and then we'll return this. Okay, and then 13W here was the current last node, so we'll transfer whatever is here from 13W to the root. Okay, so we'll overwrite whatever was at the root. So 13W is already at here, and then this node will be removed. So now 7Q will only have one child, which is 11S. Okay, now we're at 13W. We'll have to compare it with one of its children. So is it 5 or 6? Well, we'll have to compare it with 5 because that is the one with the lesser key. So 5 and 13, should we swap them? Well, yes, because 5 is lesser than 13. So we'll swap them here. And so in panel D, we already have 5 at the root and 13 at the child position. But we won't stop there, right? So at 13, we'll have to compare it with one of its children. So should we compare it with 15 or 9? Well, we'll compare it with 9 because it's a smaller key. So compare 13 and 9. Should we swap them? Well, yes, because 9 has a smaller key than 13. So on the next slide, 9 and 13 are swapped. So now 9 is already at this position and 13 is here. But we won't stop yet, right? So 13, compare it with one of its children, 14 or 12. So we'll compare it with 12 since it's lesser, right? So 13 and 12, should we swap them? Well, yes. So we'll swap 12 and 13 here, and then 12 is here, and then 13 is here. And then 13 is already a leaf node, so we'll stop since there are no children anymore. Okay? Now, how about if we do another remove min? Okay? So what will happen? So we'll remove 5a. So that would be what we'll return. And then we'll replace that with the last node, which is 11s. So this one will be removed already. Okay? Now 11s would be replaced with or compared with 9 or 6. So it has to be compared with 6, right? Because 6 is less than 9. So 6 and 11 should be swapped because 6 is less than 11. So here, that would be 6z, and then this would be 11s. But then 11s would have to be compared with one of its children, 7 or 20. So it has to be 7 because 7 is less than 20. And then 7, compare that with 11. Well, we have to swap it. So 11 will be placed here, and 7 will be placed here. Okay, so that is now your new heap after removing the min, which is 5a. So 6z is at the root, and then you have 7 here, and then 11, and 20. Okay, so that is the example of removing with down heap algorithm. Okay, so yeah. Now how about the performance of removal? So at the worst case, we will do swapping from the root all the way down to the last level. So that will also take the whole height of the heap, right? So the running time would be O of h, where h is the height. But as we mentioned, height is log of n base 2. So the removal running time will also be O of log n base 2. Okay? So this is better than the removal of unsorted DLL, because remember, from unsorted DLL, it was just O of n because we had to traverse to find the actual min, right? So yeah, in removal, finding the min is easy, but rearranging the items after removing to keep the min heap property is what takes log of n base 2. Okay, so that is insertion and removal in heaps. Okay, so now let us see how to use heaps in priority queues. Although I have alluded to it in some of the discussions earlier, so this should be quite straightforward for our discussion. So we can use heaps to implement priority queues. So we'll store the entries of priority queues in the heap nodes. And we'll keep track of the root and the last node. So we'll keep two references or variables for the root and the last node. So for the root, we have to keep track of it because, of course, we use that for min and remove min. And then for last node, we also need to keep track of it because we use that to find where to insert. And also, in remove min, we also swap the last node with the root's entry. So that's why we also need to keep track of the last node, right? So these two are the important, the root and the last node. So we keep references to it. Now, for the performance of the heap priority queue, insert will run in O of log n because it uses the up heap algorithm. So since heap insertion runs in O of log n, then that would also be the running time for priority queue insertion. And then for remove min, since removal in heap runs in O of log n because of the down heap algorithm, then remove min will also run in O of log n. However, for min, this will only take O of 1 or constant time, since we will just look at the roots entry and then return it, right? Because we won't need to remove it. We just peek at it, right? Look at it and then return. So it's just constant time, O of 1. Okay? So that is the performance of your heap priority queue. So insert and remove min will take O of log n, and then min itself will be O of 1. Okay? Now, if we use an array to implement your heap priority queue, so remember, heap is just a binary tree, right? And we've already discussed the array binary tree implementation and then the linked binary tree implementation. So this should be familiar to you already. So if you have an array implementation of the heap priority queue, it will look like this, right? So 5, 7, 9, 14, 10, 21. So as usual, the root will be at index 1, and then the child would be at index 2 times the parent, and then so let me write that down. So root is at index 1. The left child would be at 2 times the parent index, and then the right child would be at 2 times the parent index, and then plus 1, right? So that's why you have 7 here at index 2, because 1 times 2 is 2, and then this one is 1 times 2, 2 plus 1, so you have index 3. Okay, so and since this is a complete binary tree, then array cells would be filled in order, right? So the next one will be added here, so it would be added at this one, and then after that would be here, so that would be at index 8, which is here, and then after that would be at here at index 9. So the array cells will actually be filled in order, okay, for array heap. So root at index 1, and then the last node would be at index n. So if there are n entries, so if there are how many 6 entries here, 1 2 3 4 5 6, so the last node would be at index 6 also, okay, because we always leave index 0 empty, right? And then where to insert could be at index n plus 1, because the next available position would always be the immediate right of the last node, right? So if the last node is at index n, so the immediate right of the last node is at n plus 1. So for example, here the next one is at index 7, and then after that, if the whole level is filled up, it would be at index 8, because it would be added here, right? So 4 times 2 would be at index 8, and then 4 times 2 plus 1 would be at index 9 after that. Okay, so it's actually pretty easy to figure out where to insert the new entry, because it's always at index n plus 1. Okay, and then the last node would be at index n, because remember, we need to keep track of the root and the last node, right? So the root will always be at index 1, the last node would be at index n, where n is the number of entries in your priority queue. Okay, so that is array implementation of the heap priority queue. Now how about if we use the linked version of the heap priority queue? So we always have a reference to the last node besides the root node. Now how do you find the position to insert the new node? So earlier it was easy because you can just go n plus 1 in array, but how about in the linked heap? Okay, so how will we do that? So for example, here, if this is the last node, we have to insert it on the immediate right, which is here, right? But if this is the last node here, 10, the immediate right is all the way to the other branch, which is the left child of 9. Okay, so is there a way for you to do this systematically? So in fact there is. Okay, so this is the algorithm to find the insert position for linked heap priority queue. So you start from the last node, and then you repeatedly go up if the node is not yet a left child. Okay, but if it's already a left child, then you stop. Or if you have reached the root, then you also stop, because there's no way that you can go up from the root. Okay, if you found the left child, then you go to its sibling, the right child. But if it has no sibling, then you can insert it there. Okay, since it doesn't have any right child sibling, then you can insert it there. But if you are currently at the right child, or if you are currently at the root, then you continuously go down, keeping it left. So left na down. So you go to the left child always until you see a node that has no left child. And once you see that node, then you insert there. Okay, so let's build a linked heap priority queue from scratch. So at the start there is nothing, right? So this will just be the root node. So we'll just build a root here, and then after that, so this is also the last node, right? So starting from the last node, we'll go up until we either see a left child or find the root. But this is already the root, so we won't go up anymore. And then at the root, we continuously go down until we see a node with no left child. But this node has no left child, so we'll just insert the next node here at the left child. Okay, and now this is our new last node. Okay, so if we want to add the next one, so starting from this last node, we go up until we find a left child, but this one itself is a left child. So what we'll do is we'll go to the right child, which is supposed to be here, but there is no right child, so it is safe to insert the next node here. So we'll add it here, right? So now this is our new last node. Okay, so from here, go up until you find the left child or the root. So this is not a left child, so you'll go up, and then this is the root, so we'll stop. And then at the root, continuously go down until we see a node with no left child. So from the root, we go down, and this is a node without any left child, so we'll add the node here. Okay, and then now this is our new last node. And then after this, go up until you find a left child, but this is already a left child, right? So go to the right child, which is the sibling, but there is no right child, so it's safe to insert it here. Okay, so this is now our new last node. So from here, go up until you find a left child. So when we go up, we find that this one is actually a left child, right? So it's a left child of the root. So we'll go to the right child sibling, and it's here, and then go down until you find a node with no left child. So it's actually, this one has no left child, so we can just add it here. So this is our current last node. So from here, we go up until we find the left child, but then this is already a left child itself, so we'll go to the right child sibling, but there is no right child sibling, so we can just safely add it here. And then we'll just do maybe 2 more. So from here, this is our new last node. Go up until we find the left child. Well, this is not a left child, this is also not a left child, so we found the root, and then go down keeping left until we find a node with no left child. So when we go down, it has a left child, but this one has no left child, so this is safe to add it here. And then from here, we can just when we go up to find the left child, this is already a left child, so you can just go to the right and then add it here. Okay, so that is the process for finding the correct insert position starting from the last node. Okay, so yeah, So what is the difference between the two implementations for array, using array, and using the linked structure for heap priority queues? So for array, you have a slightly faster insert because you can immediately go to index n plus 1 and know that that is where you need to insert. Whereas in linked heap priority queue, you still have to do the going up and then going down to find the correct insert position, the one that we did in the previous slide. Okay, so array is slightly faster in this regard. But the advantage of the linked heap would be that it has better memory, because of course it's always the problem for array that you have to predefine the array capacity and make sure that the capacity is big enough to hold all of the entries that you have. And so when you have a bigger capacity and then there are only few entries, then that would be wasted memory. Whereas in linked structure, you add nodes as needed. Okay, so however many entries you have, that is also the number of nodes in your linked structure. Okay, so it has better memory usage. Okay, so that is the difference between the two underlying implementations for the heap priority queue. Okay, so it's an implementation of an implementation. Okay, so let's move on. So finally, let's compare the three priority queue implementations that we have seen so far. So for unsorted DLL, the insert is O of 1. It's constant time because we just insert it at the back, right? So since we don't care about keeping it sorted, we can just insert it at the back for constant time. However, removing the min and finding the min will take O of n because it will entail linear search from head to tail guard to find the minimum entry, right? For sorted DLL, insert will take O of n because you have to do the linear search to find the correct position to insert that entry into. Okay, because you have to keep the DLL sorted. But the advantage is that for remove min and min, you can always find it at the front of the DLL because you kept the DLL sorted. So doing remove min and min will just take O of 1 constant time. Okay, and then for the heap, insert will run in O of log n because of the upheap algorithm, wherein you add the node after the last node and then do the upheap to keep the min heap property. And then for remove min, you remove the root's entry and then you replace it with the last node's entry, and then from the root you do the down heap algorithm. Okay, so that's also log of n because this two at the worst case could take the whole height of the tree, and the height of the heap is log of n base 2, right? So that's why both run in O of log n time. Whereas the min, on the other hand, will just run in O of 1 because you can just find that at the root of the heap, right? So it's always at the root of the min heap. Okay, so those are the implementations for your priority queue. Now, the last thing that I want to discuss is how to actually construct or to build the heap from scratch. Okay, so given that you have keys and entries, how do you build the actual heap from scratch? Because from the examples that we've seen so far, the heap is already there, right? But how do we actually construct them if we do it from scratch? So there are two ways that you can do this. You can use the top-down construction or the bottom-up construction. Okay, so let's take a look at each one. So the top-down approach is an online approach, and that means that the keys are added to the heap as they arrive. Okay, so if it's online, that means that even if the application is already running, okay, you can still add more keys to it. Okay, even after you have already built the initial heap. Okay, so you can still add more as they arrive. And if you have a heap with n entries, that amounts to n insert operations because you add each entry each time, right? And so the running time when you build the heap in a top-down manner is n log n, because if you have n insert operations, So we have n times insert operations, and then each insert runs in O of log n time. So that's why you have O of n log n time for the top-down operation. So yeah, that's top-down. So I'll show you an example in a while after we discuss the other way to build the heap, which is bottom-up. So the bottom-up approach, on the other hand, is an offline approach. When we say offline, you must know all the keys in advance. Okay? So before you build the heap, you must know all of the keys already. Okay? So unlike top-down, which is online, wherein you can add more keys later, here, once you've built the heap, you cannot add any more because the bottom-up approach does not allow it. So all of the keys must be known in advance, and then you build it using heap merging. So we'll be doing a series of merges with the keys, okay, to keep the min heap order property. And this one actually runs faster, O of n. So for top down, it runs in O of n log n. But the advantage is that it is online. Okay? For bottom up, it runs faster in O of n time, but the drawback is that it is offline. So you have to know the keys in advance. So here, in top down, there is no such restriction. Okay, so the reason why it's faster is because you know what the keys are. Okay, so let's see how bottom up actually works. So for bottom up, let's say that these are our keys: 14, 7, 21, 3, 10, 9, and 5. So we'll start with, so since there are 7 keys here, so this will be the structure of our heap, right? So 1 and then 2 children, and then after that at the next level we have 4. So we start with 14, 7, 21, and 3 here at the bottom. Okay, and then after that, so this one are done, right? And then after that we have 10 and 9. So we put 10 and 9 here. But then when we put it as a parent of one of the nodes, we have to make sure that the min heap property is enforced. So we have to check which one is the smaller child. So it's 7. So we'll have to compare 10 and 7. Do we need to swap them? Well, yes. So we do the swap here, 7 and 10. And then here with 9, which is the smaller child, 21 or 3. So it's 3. So we'll compare 9 versus 3, and then we'll have to do the swap. So now 3 is at the top, and then 9 is here, and then 7 is at the top, 10 is here. And after that, the last one that we need to add is 5, which will be added here. And then we have to compare it with its children. So which one is the smaller one? It has to be 3, right? So compare that. We need to swap 3 and 5. So that's why 3 and 5 are swapped. But then from 5 here, we also need to swap it. Not anymore because both 9 and 21 are greater than 5. Okay, so that is how you do bottom up. So you start at the bottom, and then you add nodes at each level, and then while doing so, make sure that min heap property is still being enforced. Okay, so that is bottom up approach to building a heap. Now let's do the same thing, but this time for top down. So the same keys, but for top down. Okay, so let's start with a blank heap, and then we add 14, right? So if it's 14, so it's just this one. And then next is, if we add 7, so where will we add it? So we add it on the left child, right? 7. But then we have to check whether we need to swap. And yes, we do need to swap. So this has to be 7 here, and then 14. So that would be 7 and 14. This is our new heap. So these two are done. After that, we add 21. So we add it on the right child. And then do we need to swap 21 with 7? Well, no. So that's fine. And then we add 3. So we'll add that on the next level here. Now, do we need to swap 3 with 14? Well, yes. So this will be 14. This will be 3. And then, do we need to swap 3 with 7? Yes. So this will be 7. This will be 3. So this will now become 3, 7, 21, and 14. Okay. After that, we'll add 10 at this part here. But then we don't need to swap because 10 is actually greater than 7, which is its parent. So that's fine. And then 9 here will be added at this position. And then do we need to swap 9 and 21? Well, yes, because 21 is greater. So 21 should be here, 9 should be above. And then do we need to swap 3 and 9? Well, no, because 3 is less than 9. So the new heap would be 3, 7, 9, 14, 10, and then 21. Okay? And then finally, we add 5. So we add it here. But do we need to swap 5 and 9? Well, yes. So 5 is here, 9 is here. And then do we need to swap 5 and 3? Well, no. So our final heap is actually 3, 7, 5, 14, 10, 21, and then 9. Okay, so that is our final heap. And then let's just compare it with the one that we made through bottom up. Well, it's actually the same, right? So whether you use bottom up or top down approach, it doesn't really matter. It just boils down to preference and also the situation. Well, if you already have the keys in advance, then it's much better to use bottom up because it will save you time. It's just O of n. But if you don't know the keys in advance, if it's going to be an online application, like you still need to add more keys after you built the initial heap, then top down is the safer route because it allows for you to add more keys as needed. Okay, so yeah, that's top down versus bottom up. Now, if you want to practice doing the top down and bottom up heap construction, you can do so by pausing this video right here and trying the bottom up approach for the following keys. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 keys. So it should look something like this. The tree or the heap should look like this. So 1, 3, 7, 15. So it should be a full binary tree with height of 3. Alright. So pause the video now and then try to work on the bottom up approach, and then we'll resume the video to show the solution in 3, 2, 1. Okay. So for the solution, we have the following. So this is the structure of the tree. So we'll have to put the first, so we have 2, 4, 6, 8 nodes at the bottom level. So we'll put the first 8. So 2, 3, 4, 5, 6, 7, 8. So we'll put the first 8 nodes at the bottom. So no problem so far. After that, at the next level, we have 4 nodes. So this is the next 4 nodes, 25, 9, 11, and 17. So 25, 9, 11, and 17 are placed here. But at this point, we have we need to do some checks, right? So 25, should we swap it with 15? Well, yes. So that's why you have 15 here and 25 here. Now, how about 9? Should we swap it with 4? Well, yes. So that's why 4 is here and 9 is here. Now 11, should we swap it with 6? Yes, so 6 is here, 11 is here. And then 17, should we swap it with 20? Well, no, because 17 is less than 20. Okay, so 17 is still here. Okay, after that, we need to add the next ones, which are 5 and 8. Okay, so in the next slide, we have this. So 5 and 8 are added here, but at this point, we also need to check. So from 5 here, should we swap it with one of its children? This time 4 will be compared. So 5 and 4 should be swapped. That's why 4 is here and 5 is here. And then for 8, compare it with one of its children, it will be 6, right? So should we swap them? Yes. So 6 is here, and then 8 is initially here, right? But then 8, should we swap them with one of its children? 7. So it's basically a down heap algorithm, right? So we continue going down until we reach a leaf, or if we have found no violations. So 8 and 7 can still be swapped. So this should be 7 here and then 8 here. So that's why we have 7 all the way here and then 8 here. Okay? And then finally, the last node is 14 all the way up here. And then 14, should we swap that with 4? Well, yes. So 4 is here and then 14 is here. And then 14, should we swap that with 5? Yes. So 5 is here, 14 is here. And then 14, should we swap that with 9? Yes, so 9 is here and 14 is here. So the final heap after the bottom-up construction is 4 at the root, and then 5 and 6 as its children. And then from 5, you have 15 and 9. From 15, you have 16, 25. From 9, you have 14 and 12. From 6, you have 7 and 17. From 7, you have 11 and 8. And from 17, you have 23 and 20. So that is the final heap from the bottom-up construction. Now you can also try this with top-down construction, like starting from this key and then you add this key and then and so on until you reach the final one, and then check if you can also build a tree that's similar to this, okay, using top-down, meaning it's online. Okay, so that's it for heap construction, and that is also it for the video. So to review, we have discussed the following in this video. So we discussed priority queues, which are basically queues that follow the smallest key first out principle. So it's not first in first out anymore. It actually relies on priority levels, okay, based on the smallest key. Okay, so you have the insert method, find min, or just the min method, and then the remove min method. Okay, and then we talked about the two basic implementations of priority queues using the sorted DLL and the unsorted DLL, and then they have their own advantages and disadvantages. Sorted DLL is good when you have frequent searches or removals of the min, right? So since it's sorted, you can always just find that at the front. Whereas for unsorted, it's good for when you always have insert operations and then just rare min or remove min operations. Okay, and then we also talked about heaps, which are another data structure that's used to implement priority queues. And then heaps are basically just binary trees that follow the complete binary tree property and min heap order property. Okay, so the root will always have the minimum key, so it's easy to find where the minimum is. And then when you do insertion, insert it at the after the last node, but then you have to make sure that you do the up heap to keep the min heap order, and then do the same for deletion, right? So replace the or swap out the entry from the last node and then insert that to the root, and then do down heap to keep the min heap property implemented. Okay, so that's it for this video. So far we have discussed linear ADTs and non-linear ADTs in ComSci 123. So in the first part of um, for subject, we talked about linear ADTs. So we saw things like stacks, queues, double-ended queues or decks, vectors, lists, and sequences. And then we used the following data structures to implement them, like the arrays, the singly linked list or SLL, then the doubly linked list or the DLL. So an ADT is linear if it has a unique first element, unique last element, a unique predecessor for each item, and a unique successor for each item, right? But if any of these four properties or rules are not followed, then it's automatically a non-linear ADT, which was the focus of the second part of our course, right? So for the non-linear ADTs, we saw the maps and dictionaries, which store entries or key value pairs. The difference being that maps have unique keys, whereas dictionaries have or they allow entries with the same keys. Okay. And then we also saw trees, which are hierarchical structure, okay, nodes with parent-child relationships, and then binary trees are a special types of trees with at most two children called the left child and the right child. And then in this video we discussed the priority queues. Okay, so those are the ADTs, the non-linear ADTs that we have seen so far. And then later on we'll also see another special type of trees called the binary search trees, but that's just another extension of the trees. And then we also added more data structures to implement this non-linear ADTs. So we still used arrays and SLLs and DLLs, so just like what we did when we implemented linear ADTs, but we added more data structures. We introduced new data structures like the hash table to implement your maps, and then the skip list to implement ordered maps, and then the heap to implement your priority queue. Okay, so that's it for the non-linear ADT discussion. If you have any questions, please don't hesitate to ask me, and I will see you in the next video.